Hello，各位同学，我们今天是线上授课哈，等一下10点10分会开始。那大家看得到我的投影片，然后听得到我的声音吗？先做个简短的测试。好，谢谢。好，那我们等会应该就是准时10点10分开始上课。Good morning, everyone. Welcome to attend today's lecture. I'm the instructor Yan Yuling. According to NYCU epidemic prevention announcement, we decide to switch our lecture, from physical lecture to online lecture. Okay, uh, the topic of today's lecture is ensemble method. In previous lecture, we talked about several pattern recognition methodology, including a linear model for regression or classification, dimensionality reduction, and neural networks. In each of these methods, we derive one pattern recognition model to deal with one particular pattern recognition task. In this lecture, we are going to discuss another category of a pattern recognition method called the ensemble method. Ensemble method. The main feature of this ensemble method is that each model is composed of several different submodels. So we can eliminate the individual bias. By combining multiple submodels, we can boost the performance, and the resultant model is often more robust to noise and can get better performance. So in this lecture, we are going to specify some famous algorithm in this category, ensemble method. Here is the outline of today's lecture. First of all, I'm going to first of all I will describe ADA boost, adaptive boosting. ADA boost is one of the most famous algorithms in the field of pattern recognition and machine learning. ADA boost is a representative method in the family of ensemble methods. It provides an efficient and effective way to combine multiple models and to boost the performance. So this is the reason why we call this algorithm as ADA boost. After talking about ADA boost, I would like to share with you one important application in my research area, face detection. So we will talk about ADA boost. We will show you how to use ADA boost to carry out the first real-time face detection in the literature. Okay, the second part is about decision trees. A decision tree is a simple and useful classification or regression methodology. A decision tree can be derived by giving a training data set. So we can train a single decision tree based on one particular data set. Based on decision tree, I'm going to specify another two famous ensemble methods called the Bayesian and the random forest. We will talk about how to use Bayesian or random forest to combine multiple complementary decision tree, and we can boost the performance of a single decision tree and make the resultant model more robust. Okay, let's talk about ADA boost. Um, ADA boost was invented by Fruin and Shapir in year 1995. ADA boost is the abbreviation of adaptive boosting. Adaptive boosting. So there are two keywords. One is adaptive, and the other is boosting. To begin with, let's talk about the definition of boosting in the second item. Boosting is referred to as a category of machine learning algorithm that build a strong classifier by combining a set of weak classifiers. This is a long description, but as you could see here, boosting is not a one particular algorithm. It is a particular category of several machine learning algorithms. For algorithms in this category, they perform classification with the following feature. Actually, they derive a classifier, and this classifier, we say this is a strong classifier because this strong classifier is composed of several weak classifiers. So boosting algorithm try to select and combine multiple weak classifiers to build to construct a strong classifier. And the strong classifier is often more powerful than individual weak classifier. So if we use a strong classifier to carry out classification or regression, the better performance can be obtained in most cases. In the literature, weak learner is often weak classifier is often called a weak learner in the literature of boosting. So this is a specific term, but the meaning of weak learner is exactly the same as a weak classifier. Actually, there are numerous ways to combine multiple weak classifiers, but in the category of boosting, each strong classifier is a linear combination of weak learner. We just consider linear combination of the selected weak learners. Eta boost is one particular instance of a boosting algorithm. So this is the I specify the meaning of the second keyword boosting. So in the following, let's talk about why this algorithm is called adaptive. Let's check the fourth item. Eta boost maintain a weight distribution over the training data for iterative weak learner selection. This statement is the reason why we call this algorithm adaptive. First of all, we need to have a set of training data to derive a classifier. So a layer is a set of training data. In AWS, we maintain a weight distribution. Most specifically, we assign a weight to one particular training data. The weight is used to indicate the importance of this training data. So we will assign a higher weight to training data that is difficult to classify. So through the iterative optimization process, we can iteratively select weak learner to address the most difficult training data. So this is the reason why we say this model is adaptive, because the process is adapted to select the weak learner to focus on some particular difficult training data. So I have specified the feature of ADA boost, adaptive boosting. The resultant strong classifier perform classification based on weighted mode of the selected weak learner. So as you could see, the decision rule is simple. The strong classifier itself doesn't work. We will use the selected weak learner or the weak classifier to perform classification. Since each weak learner has its own prediction, we can compute the weighted mode of the prediction result by the selected weak learner. So this is how to make the decision. In this slide, let's talk about notation of ADA boost, so we can more specifically define the behavior of ADA boost. In this slide, I use capital H to denote the strong classifier, and I use lowercase h to denote the weak learner. There is a subscript here. The subscript of a strong classifier is used to indicate the number of weak learners. So capital T here is used to indicate that there are capital T weak learner merged to construct this strong classifier. And there is a subscript in the weak learner. It is used to index the weak learner. For example, H1, it means that this is the first selected weak learner. So it's H1. Similarly, H2 is the second weak learner, and the H capital T is the capital T weak learner. So for simplicity, we consider binary class classification problem. So given a particular data, it could be training data or testing data, we fit X into each of the weak learner, and weak learner perform binary class classification. So the output of h, lowercase h of the weak learner is either -1 or +1, negative or positive, because we are dealing with a binary class classification problem. So let's look at the definition of the resultant strong classifier. As mentioned in the previous slide, we say this strong classifier is composed of several weak learners, and actually it is a linear combination of the selected weak learner. So we use HT to denote the T selected weak learner. Alpha T is the associated weight. So alpha T is used to indicate the importance of HT in the weighted vote. Okay, so let's look at the value inside the parentheses. Actually, this is the weighted vote of the weak learner on some particular input data point X. Okay, since we are dealing with a binary class classification problem, we apply sign operator here. In other words, if the decision value is positive, this data point is predicted as positive, otherwise negative. A sign operator is very similar to employee. Is very similar to include a threshold with zero value with a value of 0. So this is the resultant strong classifier. Please remember this formulation. We will use this H, capital H, and lowercase h, and this formulation in the following. Okay, so weak learner and the strong classifier perform binary class classification. So as you can see, for weak learners, the output of a weak learner is either -1 or +1, so it performs binary class classification. For the strong classifier, since there is a sign operator here, so the output of the strong classifier is also +1 or -1. So it is also used for binary class classification. In the literature of AWS, each weak learner is required to perform slightly better than random guess. So it is qualified, such a weak learner is qualified to be used to construct a more powerful strong classifier. Okay, we know random guess is that we don't consider the data point feature vector. For given a data point as input, we random guess its label. So its accuracy is about 50% if we consider a balanced two-class classification problem. For each weak learner perform better than random guess, it is qualified to be used to construct the strong classifier. Okay, so the strong classifier actually is a weighted combination of the weak learner, as you could see in this equation. This is a linear combination of the weak learners. Okay. In this slide, let's talk about the details of weak learner. As you could see, AWS can derive a strong classifier. And this strong classifier is composed of a set of a weak learner. The question will be how to select a small subset of weak learner and how to combine them and how to determine their importance, how to determine the value of alpha. Okay, so in the literature of AWS, each weak learner learns by consider one simple feature. I know this term may be ambiguous, but this term in the literature of AWS is not ambiguous. We often consider a data point as a feature vector. So each feature vector have many dimensions. Each dimension is called a feature. So if you are dealing with a data set with 100 dimensions, we say each data point has 100 features. So each weak learner can control its decision boundary or to control its classification behavior by considering only a single features. Okay. Our goal is to derive a strong classifier with capital T weak learner. So our question is how to choose T most beneficial and powerful and even complementary feature for classification. So to answer this question, there are a lot of related questions. How to define features. So actually, this is application dependent. How to express its data point as a feature vector. So it is less relevant to AWS, but you need to give the representation of the data point you are dealing with. So after define the features of all the training data, how to select a small subset of beneficial and complementary features, how to construct the weak learner, how to manage the weight of the training data, and how to associate the weight to each of the weak learner. There are several related questions. I'm going to show you an example how AWS work, and in this way we can answer each of these questions. Please remember that in AWS there are two types of weight. The first weight is used over the training data. Each training example is associated with the weight. It is used to indicate the difficulty for handling this training data point. We also maintain a weight to each selected weak learner. For weak learner HT, there is associated weight alpha T. So there is a second type of weight which is over selected weak learner. I'm going to specify the notation later. Before talking about the AWS algorithm, we use animation to demonstrate the idea of AWS. So you can realize you can realize the rationale and the intuition of ADA boost. So let's consider a two-class classification problem. Each circle is used to indicate one particular training data, and the color of this circle is used to indicate its category, its class. So this is a two-class classification problem, class red and the class blue, each and each training and each class has 4 data points. Please notice that the radius of each circle, is used to indicate the weight of this training data. So in the beginning, as you can see, all the training data have the same weight because we have no prior knowledge about which training example are more important or are more difficult. So in the beginning, we assign the same weight to each of the training data points. We often say that this is a uniform weight distribution because all the data points have exactly the same weight in initialization. For classification, so this is the decision boundary of the first selected weak learner. This is weak learner number 1. The weak learner is a linear classifier. So this is the decision boundary. As you could see, this data set is not linearly separable. So every weak learner makes some mistakes. So as you could see here, the region below the decision boundary is used to indicate the decision region of class blue. So this data is misclassified. Similarly, the region above the decision boundary belong to class red. So these two group points are misclassified. As mentioned previously, we say we maintain a data weighted distribution. We can highlight the data difficult to classify. So in this case, we increase the weight of these three misclassified example. So in this situation, the 3 data points are more important because they are associated with higher weight. So based on the weight distribution, we can select the second weak learner. The second weak learner should be different from the first one because the weight distribution is changed from uniform to this situation, to this case. 3 of them have a larger weight. So this is the decision boundary. This is the decision boundary of the second weak learner. As you could see, because the 3 data points have higher weight, so this decision boundary correctly classifies the 3 examples that are misclassified in the previous iteration. In this situation, the region, the right-hand side region of the decision boundary is associated with a class blue. On the other hand, the right-hand side region is considered the right-hand side decision region belong to class red. So as you can see, these 2 data points are misclassified. So we need to increase the weight of the 2 data points. So this is the weight distribution after selecting 2 weak learners. Based on this weight distribution, we select the third weak learner. Okay, this is the third weak learner selected by ADA boost. Okay, we run the algorithm three iterations, so we will get three weak learners. So let's consider the decision boundary of the first, the second, and the third weak learner by majority vote. This is the resultant decision boundary if you combine the three weak learner. So as you can see, even for a data set that is not linearly separable, we can simply derive three linear classifier to carry out this nonlinear decision boundary. And actually, the process is simple and intuitive because we just maintain a weight distribution over the training data. Based on different weight distribution, we can emphasize some training example. They are currently wrongly predicted. So the new weak learner will put the emphasis on this training data. This is the resultant decision boundary. Okay, this is the illustration about how AWS work. After giving an example, we need to trace the algorithm of AWS. This is the algorithm of AWS. As you can see, it is simple. We just use a single slide to include all the iterative process of AWS algorithm. So let's trace the algorithm. First of all, we are given M training data. We know AWS is a supervised algorithm, so we need to have labeled training data. XI is one particular training data, and YI is the label of this training data. So for binary classification, YI is either -1 or +1 to indicate the class of this training data point. As mentioned, we need to maintain a weight distribution over the training data. So let's use capital D to denote. We use D to denote the data weight distribution. There is a subscript here. It is used to indicate the iteration. We know AWS is an iterative algorithm. The subscript is used to index the iteration. So D1 is the data weight distribution used for the first iteration. We need to initialize its value before running the iterative process. So let's look at the meaning of this notation. D1 of I. Actually, D1 of I is set to 1 over M. So this term is used to indicate the weight of data point xi at the first iteration. Since there is no prior knowledge about which data point are more important, so D1i is set to the value of 1 over M. It means that this is a uniform distribution in initialization. So we use a uniform weight distribution. It is intuitive. If you have some prior knowledge, you can initialize the data weight in your own way. But in most cases, AWS start from a uniform weight distribution. The remaining part of AWS is an iterative process. So we use lowercase t to index this for loop. And the value of t ranges from 1 to to capital T. In other words, we want to select capital T weak learner to construct the strong classifier. Okay, so in each iteration T, there are just 3 steps. Find the weak learner and calculate the weight of this weak learner and update the data weight. So let's look at the first step. At iteration T, our goal is to determine the optimal weak learner HT for this iteration. In we have here is a weight distribution DT over the training data. So at the special case is that at the first iteration, D1 is from the initialization. For the other iteration, this data distribution is iteratively updated. So we will take the corresponding weight distribution at each iteration. So at the iteration T, we consider data weight distribution dt. This is the equation. This equation tells us how to choose the weak learner HT at this iteration. So let's look at this equation first. HT, we use argmin operator. So for every trained weak learner candidate, HJ, we want to find the weak learner candidate that with the minimal weighted error epsilon j. So let's look at the definition of weighted error epsilon j here. It is given here. So as you can see, this is a sum operator, summing over all the training data points because there are m data. So this is a sum operator for all the data points. Inside the sum operator, what we need to focus on one particular data point, xi. So this is the weight of this data point xi at this iteration t. So let's look at the indicator function here. Please notice that this parenthesis is used to indicate the indicator function. This function include a statement. If this statement is true, the output of this indicator function is 1, otherwise 0. So let's look at the meaning inside the indicator function. On the left-hand side of the inequality, this is the ground truth of this data point, yi. On the right-hand side, we apply the weak learner candidate hj to xi because this is a binary classifier, so its output is also either +1 or -1. So the inequality here is used to indicate if this data point is misclassified. More specifically, this statement is used to indicate that if Hj will only predict Xi, okay? So if wrong prediction happens, we need to compute its weight, okay? So if we consider the sum operator, as you can see, the whole term can be considered the weighted error met by Hj on the training data set. This is the definition of Hj. In the argmin operator, we want to select a weak learner with the minimal weighted error. So the weak learner selected at this iteration is this one with the minimal weighted error. Okay. So after running the first step, we know the selected weak learner HT. We also have the corresponding weighted error epsilon t. Okay. The second step. Uh, so if we want to use if you want to remember the meaning of this the first step, we choose the weak learner to minimize the weighted error. Okay, let's look at the second step. Epsilon t is the weighted error of ht, the weak learner ht. So let's calculate its weight. Okay, so as you can see, weighted error is between 0 and 1. So for a lower value, for a lower value of epsilon t, it is used to indicate that we will have a high value of ht. It is intuitive for weak learner, for selected weak learner with a very low value of weighted error, we need to have increase its importance, so its weight is larger. Also, I want to emphasize that each epsilon j or epsilon t is always less than 0.5. It's always less than 0.5. Let's talk about the reason. For binary classification problem, if a weak learner contribute a weight higher than 0.5, we just switch its output. We can reduce its weighted error. So it is impossible to select a weak learner with a weighted error larger than 0.5. So as you can see, let's look at the range of the value alpha t. Epsilon t is lower than 0.5. So the numerator is always larger than the denominator. So the fractional number, the value of this fractional number is always larger than 1. A log of the value larger than 1 is always positive. So alpha t is always positive. Okay, I will show you later. This closed form solution is derived by minimizing the so-called exponential loss. I have not defined what the exponential loss is, but I'm going to give the detail later. Finally, this is the third step is weight update. We want to update the data weight. Okay, so this is the equation to compute the updated data weight distribution. Let's look at the detail. Our goal is to calculate the weight distribution for the next iteration. Actually, this value depends on its original value in this iteration. The exponential term here is used to implement the idea. If a data point is misclassified, we need to increase its weight. Otherwise, we can slightly decrease its weight. After update, this may not be a distribution. By a distribution, all the elements should be non-negative and sum to 1. So to make this as a distribution, ZT is included for normalization. So this is the resultant algorithm. The last step is to give wrongly classified data more chance in the next iteration, because if a data point is misclassified at this iteration, we increase its weight. At the next iteration, weak learner will pay more emphasis on this wrongly classified data points. I would like to specify the Anna-Bruce algorithm in Chinese again. 各位同学，这边是Ada Bruce 的演算法哈，因为这一届的数学是比较多， 那我这边就用中文再重新讲一次哈，希望大家可以记得这一个演算法。你可以看到一个很有名的演算法，但是它却是这么的精简哦，就是说只要用一页投影片就可以把这个演算法把它讲完，所以这个演算法是相当好 implement， 相当精简的，而且呢在很多实物上面，它的效果相当的好，所以这是一个简单来说，这是为什么就是这个演算法这么热门的原因呢？又简单又好用。那我们开始讲这个演算法它的细节。那因为它是一个 supervised 的演算法，所以我们必须要有 training data 而且是有 label 的，所以总共它有 n 笔训练资料。那我们用 xi 呢代表 di 笔训练资料，那因为它是 supervised， 它需要 label。那如果我们在处理这种二元分类的问题的时候，这个 yi 呢，它的值呢，要么就是正一，要么就是负一，代表它是正负的类别。那我们刚刚有讲过，AWS 的总共要维护两种不同的权重的分布。那第一种呢，就是这种资料的权重。那我们这边用大写的 D 大 D 呢来表示这个资料的权重。你看它有一个下标这个下标一呢是代表它现在是要来做第一个 iteration 的权重那 DEI 的意思呢，就是呢第一个 iteration 里面 DI 笔资料它的权重是多少。那一开始呢，我们不知道这 N 笔资料里面哪一个比较重要，所以一个很直觉的方法就是呢，我就给它一样的权重那因为我们希望它是有一个权重的分布所谓的分布就是通通都是非负的，而且加起来等于1。所以一个很直觉的方式呢，就是呢既然有 N 笔资料，所以每一笔资料的权重资料权重就是 N 分之1。这个就是指它是一个 uniform 的这个权重的分布。我们通常都用这个词 uniform 代表它这是一个平坦的分布。我们刚刚讲AWS 的是一个就是 iterative 迭代式嘛，就是一个迭代式的一个演算法。所以呢它有若干个iteration。在这里面呢，我们假设说我们令它的 iteration 的数量是大 T 好了，那这个的意义呢，就是代表说这个 AWS 的所找出来的这个 strong classifier， 它总共呢就会有大 T 个 weak learner。那所以在每一个 iteration 里面呢，我们的工作呢就是要去找最合适的 weak learner 出来。那其实你可以看到在这个 iteration 里面，它其实也就只有3件事情要做而已嘛。就是去找它的 weak learner 出来，然后呢，去把这个 weak learner 的权重也算出来，然后呢，再去做它的这个资料的权重的 update， 就是只有这3件事背都可以背得起来这样子那所以我们来看第一个步骤第一个步骤就是决定我在第T个 iteration 的时候呢，我到底要选哪一个 weak learner 假如说我有一个很大型的一个 weak learner 的 pool， 那我要从里面挑哪一个出来呢？实际上简单来讲，结论呢就是呢，它要叫你去挑这个 weighted error 最小的什么叫 weighted error 呢？因为我们总共有 n 笔资料，那每一个资料呢又有它的这个权重的分布，所以我们希望可以找一个 weak learner 出来。那它呢，这个 weak learner 的条件选出来，这个 weak learner 的条件就是呢，它是所有的选择里面 weighted error 最小的那一个。那什么数学是来具体的表达我刚刚讲的这句话呢？它先用一个 argmin 的 operator 在这边，也就是说呢，这个 ht 是我们要选的。那它实际上呢，就是从所有的 candidate hj 里面呢，选这个weighted error epsilon j 最小的那一个，把它选到，这个选来就是在这边。那这个呢，就是呢 weighted error 第这一个 candidate weak learner candidate 第这一个 weak learner candidate 它的 weighted error 的定义就写在这个这边你可以看到这边有一个加总的符号， 那就是考虑的所有的 training data 那 M 是 training data 的总数 ，I 是 index， 所以在这个加总的符号里面呢，我们考虑的就是 DI 比资料。那 DI 比的资料，我们权重把它写在这边，然后这个中括弧这个中括号代表的就是这个所谓的 indicator function。那这个 indicator function 呢，里面呢会有一个 statement， 就是一个逻辑表示式。那如果这个逻辑表示式是成立的，是真的的话，那它的输出就是一，也就是说这个权重要被加起来的意思。那反过来讲，这个表示式呢是不成立的，那这个输出就是零。那在这边的意义就是说呢，这个权重就不用加起来。那我们来看一下这里面的这个表示式的意义是什么 ？yi 不等于 hj of xi。yi 是 DI 比资料的正确答案，它告诉你说它是哪一个类别。那 hj of xi 的意思呢，就是你把这一个 weak learner candidate 把它套用在 DI 比资料里面，因为我们知道它都是做二元分类的问题，所以它的输出要么是正一，要么是负一，所以你就可以知道它跟正确答案是不是一致。如果不一致，就代表呢它的意义呢，括号里面的意义就是说 hj 这个 weak learner 在 xi 这笔 data 上面的分类结果是失败的，它是分错的，所以分错的我就需要把它的权重考虑进来。那你就用这样子的数学式来表示的时候，就代表你把所有的 hj 所分类错误的资料的它的权重都把它加总起来，所以我们说 hj epsilon j 呢就是 hj 的这个所谓的 weighted error。那你今天你有不同的 weak learner candidate 嘛？那你总是可以在这些 weak learner candidate 里面去挑一个你最好的结果出来，这样。那在这边要跟大家补充一点就是说呢，这个 epsilon j 它的值有没有可能超过 0.5 呢 ？epsilon j 的值有没有可能超过 0.5？ 我们知道这个权重的分布它是一个分布，它是一个 distribution， 所以呢错最多就是1，然后呢错最少就是0，就是这样子。那在这种情况之下，你觉得这个 epsilon j 它有可能超过 0.5 吗？就是它的错误的权重呢比正确的权重还要高，你觉得有可能发生这件事情吗？其实呢，可以透过一些简单的机制就可以避免这个事情就是说呢，今天呢，如果有一个 weak learner 他这样子计算了以后呢，他的权重呢，他的错误的权重，他的 weighted error 居然高达 0.6 就是分错的比分对的还要高。那在这样子的情况之下呢，其实你只要呢，这个 weak learner 都不要动，你只要把它 swap 它的这个输出，就是呢，它原来预测成1的，你就把它变成-1，那原先是-1的，你就把它预测成1，那这样子它的权重，它的这个 weighted error 就变成0.4。所以呢，我们这边要讲的事情就是说呢，如果你的这个 weak learner 的 pool 够大的话，这个 epsilon j 呢是不可能超过这个不可能超过这个 0.5 的。你这个选出来的这个 weak learner， 它的这个 weighted error 是不可能超过 0.5 的。也就是说呢，它是比 random guess 还要好你随便猜，你期望值错误的期望值就是 0.5。那它这边呢，就是说你始终都有一个机制，就是说你一旦找到了这个 weak learner 呢，它的这个 weighted error 大于 0.5 的话，你总是可以把它的输出，只要把它做一个转换了以后，你的输出就会小于 0.5 所以每一个 iteration 做出来的 weak learner， 它一定都比 random guess 还要好。然后呢，而且呢，它的这个 weighted error 一定小于 0.5。那我们接下来就来看第二步。这个第二步呢，就是要来决定这个 HT 它的权重因为我们知道 Song Classifier 是要对整个这个 Weak Classifier 做这个 weighted vote 就是有权重的这种 voting， 所以每一个 Weak Learner 权重是不一样高的，所以它这边呢有一种计算方式来决定，就是说这个 Weak Learner 它的 weight那这个呢，其实 这个呢其实是对于这种以后等一下我们会讲的 exponential loss 去做微分等于零的时候的最佳解。那虽然我们现在还没讲它的意义，但是呢，你也可以发现哦，其实这个数学式呢，其实也是蛮直觉的。一减掉 epsilon t 就代表它的 weighted correction，那分母呢就是 weighted error。那在这种情况之下，这个分数呢越大的话，哈，这个分子除以分母，这个分数越大的话，其实代表东西就是代表说这个 weak learner 越好嘛，因为它的 weighted error 很小这样子，所以我必须得要给它一个比较大一点的权重。那最后一个步骤呢，也是蛮直觉的，就是我们要对于这个资料呢做一个权重的 update。alpha 呢是 weak learner 的权重，D 呢是 data 的权重，这边不要搞混了。那我们来看一下哈，就是说我们现在有的权重呢是 iteration t 的，那在第 t 加一个 iteration 的时候，其实它们的关联性是写在这边，差别就是只有差在分子有一个 exponential 项，然后分母有一个 normalization term 而已。那我们先讲一下这个 exponential 的这个东西。那你也可以看到哈，这个 alpha 是一个大于零的 ，alpha t 是一个大于零的东西。那 yi 乘上 ht of xi， 基本上 yi 是正负1的值，那 ht of xi 是正负1的值，就是用来代表这笔资料有没有成功的被这一次所选的 weak learner 给分对。所以呢，根据这样子的数学式，你就可以知道，它的逻辑就是呢，你一旦分错了资料，这个 iteration 分错了资料，我就把它权重增加。那反过来讲呢，它如果是分对的资料，我就让它的权重稍微降低一些。那经过这样子 update 了以后，这个不是分布，这个东西每个都是正的，没有问题。因为原来 dti 本来就是正的 ，exponential of something 这个一定也是正的。那但是呢，这个加总起来，所有 data 加总起来，它就不见得是一个分布，加起来不见得等于1。所以我们这边呢，让它除一个例 t， 除完了以后呢，这个 dt 加1呢，也是一个 distribution。那这一个数学式的直觉的意义呢，就是呢，让这一个 iteration 呢被错误分类的这些资料呢，权重增加，所以呢，它在下一个 iteration 的时候呢，它就会比较容易去影响到下一个 iteration 要选的 weak learner， 因为它比较高的权重。那这个是这个演算法的中文的介绍。Do you have any question about AWS algorithm?
老师，可以问一个问题吗？就是AWS 那边，因为我在其他地方看到它的 weight 对 data 的 weight 是不会做几率的 normalization， 不会把它当做几率去做解释的。那想请问这边特别把它用几率去做解释有什么好处吗？
这个是必要的哦。或许我们可以再讨论你在哪里看到的版本哦，因为你没有做这种如果没有做这种 normalization 的时候，你的 epsilon t 的值域呢，就不会是介在0跟1之间，你就接下来就没有办法去决定这种1减掉 epsilon t 除上 epsilon t 的哈，可能写法不太一样，但是就我所知哈。那它应该是需要做 normalization 的，至少在 AWS 里面。那如果没有做 normalization 这个步骤，或许会需要做一些适度的调整。那这个可能就是
了解，不好意思，我看到了。如果是在 data 那边没有做那个 normalization 的话，是那个 epsilon 那边会做 normalization。
对，它一定要做 normalization 才可以算出来这种 cross-form solution。
只是因为我会有点困惑的是，这边就对 error 做 normalization 意思蛮好懂的，因为 error 有点像是我们做那个平方差，我们会把它除以 n 一样。但这边对 data 做 normalization 把它弄成几率的话，有什么特别的好处吗？
我觉得这几乎是一模一样的事情啊！你可以看到这个 epsilon， 你说你觉得对于这种 error 做 normalization， 你觉得很好理解。那 epsilon 跟 weight 是不是正比的关系？你在哪里 normalization 其实意义都是一样。如果你可以理解某一个 你觉得在做 epsilon 那 error 那边做 normalization，你觉得很好理解，那这个 d 这边做 normalization 是同样的意义，这样子。
好，了解，谢谢谢老师。
还有其他的问题吗？If there is no question, let's have a 10-minute break. So let's get started at 11:15.
老师，我想再问一下，那个 ZT 要怎么算呢、
例题这蛮简单的啊，就是你先把这边呢，这个 I 呢，它是对于所有的 data 的 index 嘛，对不对？你先把所有的 data 的这个分子的项目通通都算出来了以后，把它加总起来就是例题的这样子。
哦，对对，哦，了解了解，就跟那个 weight，所以刚才说和 weight 的分母那是一样的意思，就是反正就是把全部加起来，也不会特别去多计算什么。
就是要计算，不是不用特别计算。
对，那想问一下，那个阿法前面，有一个系数1/2，那个也是因为了要弄它 normalization 才加1/2的嘛？
这个是等会会讲，这是 exponential loss 最佳化的这个结果。那你可以看到哈，其实呢，它有没有这个1/2，可能影响也不是，可能也没有什么影响啊。因为呢，你到最后是做 weighted vote，那所有的 weak learner 前面都有1/2，好像全部的重要性都减半。那其实到最后做 voting 结果还是都是一样的这样子。不过，总之他就比较喜欢写一个1/2在前面，而且这个是推导出来的这样子。
哦，因为不加1/2，它可以把它解释成 odd 这样，就是
你说不加1/2会怎样？
是，我记得 odd 不是也是长这样子吗？
我不知道什么是 art。
好，好，那么那就是一个统计的，那可能等一下我再看看，可能再讲。好，谢谢老师。
好，OK。 Hello, let's get started. In previous section, we have talked about the algorithm of ADA Boost. We say this algorithm is simple and intuitive. However, ADA Boost has its own theoretical support. Actually, all the elements have its theoretical support. So in the following, let's look at the theoretical part of ADA Boost. Uh, First of all, I write down the strong classifier and the weak learner in the formulation of ADA burst, including H, capital H is used to denote the strong classifier, and lowercase h is used to indicate the weak learner, and the alpha t is the weight for weak learner ht in the majority vote. Okay, let's look at the definition of this term, margin. Uh, the margin of the strong classifier on one particular data point is defined in this way. H is the strong classifier. So we apply H to the feature vector of the data input data point X, and we calculate the multiplication of the label Y and the H of X. This term is defined as the margin for this strong classifier on one particular data point X, Y. So let's look at the meaning margin. Actually, meaning indicate two important properties. Two important properties of the classification result. So the first property of margin is that it is used to indicate whether the sample is correctly classified or not. If this data point is correctly classified, YH of X is larger than or equal to 0. So you can check this property by yourself. You can consider positive training data and the negative training data simultaneously. For positive training data, the value of Y is positive 1. And if what is the situation if this data point is correctly classified? Otherwise, you can consider, on the other hand, you can consider the case for negative data. So you will get the conclusion why h of x is used to indicate if this data point is correctly classified or not. Actually, this is real value. This is real value. So it is used to indicate the classification confidence. We hope to correctly classify this data point with high confidence. So we hope that the value of y h of x is large enough. And actually, this margin is defined for one particular data point. If we want to consider the whole data set, so we can calculate the sum of margin for all the training data point. Okay, this is the definition of margin. ADA Boost does not directly consider margin. Instead, ADA Boost aims to maximize the margin of all the training data while minimizing the so-called exponential loss. So there are two terms in this description: margin and exponential loss. So let's look at the definition of exponential loss. This is the notation exponential loss. Exponential loss for some particular trend, for some particular strong classifier. Actually, exponential loss is defined over all the training data. We know training data is composed of the feature vector and its label. So this is the expectation operator over x and y. So let's look at the definition of exponential loss. Let's look at the term inside the parentheses. It is exponential of minus margin. Minus margin. Please notice that exponential loss is exponential of minus margin. Y h of x is margin. Okay, so as you could see, exponential is also a monotonic function. When we want to maximize the margin, it is equivalent to minimize the negative exponential of negative margin. Okay, so this is the so-called exponential loss. Our goal, the goal of AWS is to select weak learner and determine the weight of the weak learner to minimize the exponential loss. So our focus will be exponential loss in the following few slides. In the first two items, I write down the formulation of the strong. I write down the formulation of the strong classifier and the exponential loss we just explained in the previous slide. Okay. We know AWS is an iterative process. So at iteration T, this strong classifier can be divided into two parts. The first part is composed of the first T minus 1 weak learner. This part is fixed because at iteration T, our goal is to choose a weak learner as T and determine its weight alpha T. We cannot further modify the selected weak learner in the previous iterations. So this part is fixed. And the second part is our target at this iteration, including weak learner and its weight. So let's look at the derivation for this exponential loss. I write down the exponential loss on the left-hand side of this equality, and we divide the expectation operator to over x and y respectively. Okay, so inside the first parenthesis, we consider one particular training data point x. From this equation to this one, we just substitute this equation into this one. So we can divide the strong classifier into two parts. The first part is fixed, and the second part is our target. Okay, this is the addition, an addition in the exponent. Actually, it can be equivalent expressed as the multiplication of the two exponential function. Okay, and this part is fixed. This part is fixed because y is given, so it is not the optimization variable. So this is fixed, and the second part consists of our targets, including alpha t and ht. Okay. Now let's talk about how to derive from this equation to this one. Actually, this is the expectation operator. So we can divide alpha t, ht of x into two situations. This is x is correctly classified of this part. Y is equal to ht of x. We denote its probability because this is an expectation operator. So we can say the probability of this data point has been correctly classified by st. The second part is this data point is wrongly predicted. So this is the last equation. the last equation in the top of this slide. So based on this equation, actually this is the exponential loss. Based on this equation, I want to specify the rationale of selecting ft, alpha t, and the data weight distribution. First of all, let's consider the first step in the iterative boosting algorithm. We want to choose alpha t. Which alpha t should we choose? In this expression, this term is fixed. It is irreverent to ht, and alpha t we can consider its value range. Our focus currently is ht. It is an optimization variable. We can always choose one particular ht. So let's look at the property of this equation. First of all, exponential of this term, it is proportional to the weight of the training data point accuracy. As you could check, this property can be proved by considering the algorithm of data boost. So this term is proportional to the weight distribution, and it is fixed. Okay. Now let's look at the range of this term. We know alpha is always larger than 0. I have specified the reason in the previous session. So once alpha t, although we don't know its value currently, but we know alpha t is always larger than 0. So exponential of minus alpha t lies in 0 and 1. So as you could check, exponential of a negative value, so it is always, the value is always between 0 and 1. And the exponential of alpha t is larger than 1. So as you could see in this equation, this term exponential of minus alpha t is less than 1. And the exponential of alpha t is larger than 1. Okay, so this value is larger than this value. So our goal is to minimize the exponential loss. So as you could see, our goal is to select a weak learner with this probability can be maximized. This probability can be maximized, okay, because this value is less than this one, okay. So according to this expression, we can realize that if we want to maximize this probability, it means that we need to minimize the weighted error. Weight is here. We want to minimize the weighted error such that we can minimize the so-called exponential loss. So ht at timestamp t, we select the weak learner as t. That is with the minimal weighted error. This selection is intuitive. More importantly, this selection has its own theoretical support. If we select a weak learner that minimize the weighted error, it minimizes the corresponding objective exponential loss. Okay, so this is the theoretical support of choosing HT。这边需要讲中文吗？还是这边是听得懂？ Okay, I don't get any response. I believe most of you can understand what I say. So I specify the next part, alpha t. I also write down the exponential loss here, okay, in the top of this slide. Once the weak learner has been selected, has been selected. So we know the probability of data being correctly predicted and the probability of data being wrongly predicted. We have the value. Okay, so this is the probability we have. This is another probability we also have. Once the true probability, we get the fixed value of the probability. In this situation, we can calculate the exponential loss as the function of alpha t. In this situation, we want to minimize this objective function. The optimization variable is alpha t. So the one of the widely used choice for optimization is to set the derivative of the exponential loss with respect to alpha t to 0. This is how to set the derivative of exponential loss with respect to alpha t to 0. After solving this equation, you will get the closed form solution. So this is why we say alpha t, the value of t can be calculated by using this equation. Okay, so this is the second step. This step is also used in this step, the value of alpha t is determined to minimize the exponential loss. Okay, let's look at the last step, the third step at the iterative ADA boost algorithm. We want to maintain the data weight distribution for the next iteration. Currently, we are at the timestamp iteration t. Our goal is to maintain the weight distribution for next iteration. Okay. So after checking the ADA boost algorithm, so you can find that the training data x at the timestamp t can be expressed is proportional to this term. This term we have specified this term exponential of minus margin. Okay, so this is the weight distribution at timestamp t. After update, we hope the weight distribution could be maintained. So the only difference is that ht is replaced as ht minus 1 is replaced by ht because the weak learner lowercase ht has been selected. So this is the new weight distribution. Similarly, after update by using this equation, you can check this equation will make the resultant weight distribution similar to this part. It will become exponential of exponential of minus y ht plus 1 of x. Okay, so this is the reason why we employ this equation for update. ZT is used for normalization. So in the previous two items, I used the term proportional to. It is not exactly the same, but it is proportional to exponential of minus margin at the current iteration. Okay, so in the previous three slides, I specify ft is selected to minimize exponential loss, and alpha t is determined to minimize the exponential loss, and data weight is updated to be consistent with the exponential loss. So it turns out that ADA boost has its own theoretical support. There are three important steps at each iteration, and the resultant, the output of each step, output of the three steps include st, alpha t, dt plus 1. All of them are determined to minimize the exponential loss. So this is the reason why we say AWS has its own theoretical support because this optimization variable are used to minimize the exponential loss. So this algorithm is always converged. Okay. 我刚刚讲的东西如果没有办法 follow 也没有关系，这也不影响你们就是使用 AWS。虽然我还是希望你们可以了解。那简单，如果是用一个 high level 的叙述的方式来说的话，就是呢，我们刚刚定义了 margin， 然后我们定义了 exponential loss。那这三个输出，就是在这个 iterative 的 AWS 的演算法里面 ，HT、阿尔法 T 跟 DT 加一，这三个变数的输出呢，它的值的控制呢，其实都是直接去最小化这个 exponential loss。那简单来讲呢 ，exponential loss 跟这个训练的正确率有关嘛？因为 margin 的定义就是这样子的 ，margin 不但考虑它的正确性，还考虑它的这个信心指数嘛 ，confidence 嘛。所以如果这三个输出呢，都是直接去最小化这个 exponential loss， 所以它可以保证这个方法呢选出来的这个 weak learner 会让 training data 越来越正确，分类越来越正确，而且呢，它保证收敛。因为这个 exponential loss 不可能无止境的一直让你往下降，所以呢，你总是跑到一定的程度了以后呢，这个 exponential loss 就不会降了，或者是已经趋缓了，那这个方法就收敛。所以这个演算法它有它很好的这个性质。以后可不可以就请你直接用讲的哈？因为如果你打字的话，不见得说其他同学会看得到，然后有的时候他在我的这个荧幕里面只是闪跳过一下就过去了。有没有什么问题要问的？
老师有听到吗？
有。
老师，我想问一下，说为什么要在刚刚提到它是跟 exponential ht 是正比的，那补上 exponential 负 alpha t 是因为要把错误的放大吗？
错误的权重放大，然后呢，把分对的结果把它的权重把它缩小。
了解了，谢谢。
它同时有你看得到我的滑鼠指标嘛？那你可以看到 yiht of xi， 这简单来说就是指这个 ht 呢对 di 比资料它到底是分对还是分错？那分对的这个 y 乘上 h 这个值就是正一嘛？那反过来讲它就是负一，对不对？这边应该可以理解嘛？那我们知道 alpha t 呢都是正的值，那如果你 exponential 负的正的，然后再乘上一个正的，就分对的结果的时候，所以它乘上一个 exponential of 一个负数，那这个东西其实就是在这个值是在0跟1之间，所以它会把它的权重降低。那反过来讲如果你的 yi 乘上 ht of xi 是正一的话，代表它是负一的话，代表它分错了。那一个负的东西再乘上一个正的 alpha t， 再乘上一个负的，所以你会得到的一个结果呢，就是 alpha t。alpha t 是一个大于零的东西，所以这个 exponential，然后 exponential of alpha t 这个东西呢，值就会大于一，所以它会把它的权重再放大，所以它有一个放大跟缩小的意义在这边，完全就是根据这笔资料在这个 iteration 它到底是分对还是分错。
了解，谢谢。
老师，
还有没有其他问题呢？
老师，
请说，请说。
我想问21页的那个 x， 就是期望值那边的算式，就是有点不太懂。他这边是想要去算那个ht of x 的 exponential loss 的期望值。
这个数学是你看它这一连串的这个推导，我刚刚有讲它每一步是怎么推导的嘛， 那我在想说，你的问题是不是说为什么我们要写成最下面这个数学式哈？那我们看一下最下面这个数学式有什么意思？就是呢，你看前面这一项哈，就是全部都是固定住的，而且这个东西呢跟你这个资料的权重有关系，所以这一项是固定住的。那这后面呢，这个里面的就比较里层的这个括弧里面呢，才是有我们这个 iteration 要解的东西，包含 alpha t 的值还没有定，那 ht 还没有选哦，它就是只有，就是说在这个内部的括号里面呢，才是这些未解的东西。那我们就是要考虑到这个里面的这些东西的，来决定，就是说它到底 h 要选哪一个比较好，那 alpha t 值要怎么决定比较好。我不晓得这样有没有回答到你的问题，还是你要问的是？
想问就是倒数的第2行跟最后一行是怎么变成那样子？
因为呢，这一边呢，就是说它的这个是 expectation 嘛，就是对所有的 label 的 y 它要做考虑嘛。那这个呢 y 在这边，而且这后面的这些东西都是固定的，那你就把它的这个2种情况都考虑的情况之下，你就可以把它搬出来了。每一个 x 你都是有它固定的 y 嘛，所以你就可以把它这个东西搬出来啊。那这个 x 还是在外面。那这边呢，这里面呢，这里面为什么这边变成是一个 probability 呢？主要原因是因为 h 我们还没有决定，那我们要想要把它分成是分错的跟分对的。对 x 这笔资料来说呢，分错的 ht 跟分对的 ht 啊，那因为呢，它这边有一个这边有一个expectation operator， 所以这边呢就是有一个 probability 在这边。我想这个呢大概你看得懂意思就好了，因为其实呢到后面呢它的计算呢所有的 training data 都是 discrete。然后呢，分对分错2种 case 也是2种 discrete case， 所以你只要对适度的对这东西做加总，这样就好。
所以它就是对每一个 iteration 找出最适合的那个 weak learner。
对，
但是它这样子怎么能保证所有下来是最好？
因为它可以选的 weak learner 哈，我们后面会讲一些例子，就是说 weak learner 你可以想象说，我有一个 weak learner 的 pool， 就是说呢，他已经事先都已经决定好了 weak learner 有哪一些可以选，那你就是从里面呢选一个可以让这个数学是最小化的，这样就好。如果你都选不到可以让这个数学是最小化，那代表你大概已经选不下去了，再怎么选也不会 improve。可是就像我们刚刚所说的，所有的 weak learner 它的 weighted error 一定都是小于 0.5， 所以你就算是很接近 0.5 了，你还是可以选让它这个再下降一些些，只是下降的东西有边际效应的关系，那它可能不见得选下去会有帮助。
好，谢谢老师。
还有没有什么其他的问题我可以回答？OK， so finally, let's look at an example of AWS. In this example, I want to show you the power, the effectiveness of AWS for data classification. So let's consider a binary class classification problem. So as you could see in the distribution, we know the decision boundary should be nonlinear with respect to the input space. And you might notice that some blue point and some red point mixed together. So this is a challenging classification problem. Okay, so let's look at the behavior of AWS. How AWS combines several linear classifiers to carry out nonlinear classification. Okay, so this is the given data set, training data set for binary class classification. At the iteration, at the first iteration, this is the decision boundary of the first selected weak learner. So this is a linear decision boundary. So the weak learner itself is a linear classifier. Okay. So based on this decision boundary, we can plot the decision region of the two classes in the input space. I use a green shaded region to indicate the decision region of class rate. Similarly, I use a yellow shaded region to indicate the decision region of class group. So this is the output of the first iteration. Okay, I enlarge the decision boundary and the two decision region after choosing the first weak learner. Okay. After choosing the first weak learner, we can update the data where we increase the weight of the data they are misclassified by the first weak learner. So after data weight update, it is allowed to select the second weak learner. So this is the decision boundary of the second weak learner. The first one and the second one. You might notice that the decision region remained unchanged. The first decision, the decision regions at the first iteration and the decision regions at the second iteration. You might notice that the decision region remained unchanged. Let's look at the reason why. We say H1 is associated with weight alpha 1. Similarly, H2 is associated with weight alpha 2. If alpha 1 is larger than alpha 2, in this situation, we just have two weak learner, and the alpha 1, the value of alpha 1 is larger than the value of alpha 2. The weak learner H1 will dominate the result because we use the weighted vote. They are just the two voter, and voter number one has a large weight, so it will dominate the result. So this is the reason why decision region remained unchanged. If we include the third weak learner here, so the decision boundary change, we can increase the region, the green shaded region. Okay, so this is the decision region after choosing three weak learners. Decision region after choosing a 4 weak learner, 5 weak learner, 6 weak learner, 7 weak learner, and the 40 weak learner. So this is the resultant decision boundary if we use ADA boost to choose 40 linear classifier. So as you could see, here is the decision boundary. It is highly nonlinear, but the nonlinear decision boundary is constructed by using 40 linear classifiers. So as you could see, this ADA boost with just a few weak learner, it can have some satisfactory result on the training data. Okay, so this is an example. In the following, I'm going to specify how to use ADA boost to carry out phase detection. We know ADA boost was invented by Furen and Shapir in year 1995, but the algorithm is not very popular at that time. In year 2001, two computer vision researchers used ADA boost to carry out the first real-time phase detection algorithm in the field of computer vision. So ADA boost become more and more popular. many researchers in the field of artificial intelligence use ADA boost to control their algorithm to facilitate their applications. So let's look at which algorithm make which paper make ADA boost very popular. First of all, let's look at the definition of face detection. Given an image as the input, the goal of face detection is try to identify and localize the regions of the region of a human face. So take this image as an example. There are 11 faces in this image. So this is the perfect face detection result because all 11 faces are detected and there is no false positive. For each detected face, we can use a rectangle or a square to indicate the size and the location of this face. Face detection can be very challenging. Take this image as another example. As you could see, we need to detect a large face and small faces. Also, this face is quite blurred. It increases the difficulty of face detection. Here are more challenging example. We need to consider different lighting condition and different image quality. Okay. Via this slide, I want to let you understand a face detection problem is often carried out by using binary class classification. Actually, detecting faces in the image is reduced to numerous binary class classification problems. So face detection is often carried out by a sliding window algorithm. What is the meaning of sliding window? Take this as an example. First of all, let's consider the blue square here. The blue square covers a sub-image. We use some feature extraction method to extract the feature. So we can use a vector to represent this window. And this vector is fed into a binary classifier. This classifier is used to separate the face from non-face pattern. So it is a true class classification problem. The positive class is face, and the negative class, the negative class is non-face. Okay, so this is a binary class classification problem to determine if this window is a face or a non-face pattern. After carry out binary classification on this window, we slightly shifted the window toward right-hand side, so we get the second window. We apply the same procedure to determine if the second window is face or non-face. Similarly, we can ask the binary classifier and to check if the third window is face or non-face. So we can slide this window from left to right. Also, we move down the window and scan the second row. Okay, so this is if we scan every location, we can detect face of this scale. If we want to detect a large face or a small face, we need to enlarge the window and we need to shrink the size of this window to detect small faces. So as you can see, detecting faces in the image is reduced to numerous binary classification problem. So we sliding a window across an image and evaluating a face detector or binary classifier at every location and every scale. Okay, this is the detection result. Most of the faces are detected, but this result is not perfect because there are some false positives. This is a false positive. This is a non-face region, but the detector said this is a face, so this is a false positive. What I want to introduce is the Viola and Jones paper published in CBPR 2001. So this is a seminal approach to real-time object detection. Before layer algorithm, face detection is time-consuming. It cannot support real-time detection. With this method developed based on AWS, it can carry out real-time face detection. This is the first real-time face detection algorithm in the literature. It can carry out more than 15 frames per second on penitentiary machine. Penitentiary machine is the CPU at that time. The training process is slow, but the detection is very fast. Actually, this paper contributes three components. The first one is to use a rectangle feature. Is how to extract its own feature to facilitate face and non-face separation. So this is the flexibility of AWS because we can always choose our own way to express data. They can facilitate the classification task. The second component is AWS. How to choose a small subset of the rectangle feature to carry out face detection. The third contribution is attentional cascade. The attentional cascade is used to speed up the process of face detection. Because the third component is irrelevant to AWS. So in the following, I'm going to introduce a rectangle feature. How to express the feature of a face or a non-face window, and how to use AWS to select the best rectangle feature to separate faces from non-face patterns. Okay, let's look at the definition of a rectangle feature. It is simple. A rectangle, there are 4 types of rectangle feature, including 2 rectangle feature, 3 rectangle feature, and 4 rectangle feature. Let's look at the example of 2 rectangle feature inspired by its name. A 2 rectangle feature is composed of 2 equal size and horizontally connected windows. So the white window and the white rectangle and the black rectangle. Okay, so this is another case of 2 rectangle feature, but the 2 rectangle are vertically connected. Similarly, this is an example of the 3 rectangle feature and an example of the 4 rectangle feature. In the following, let's talk about how to use rectangle features to extract features of a face or a non-face pattern. Given a face as the input, if we apply this rectangle feature, to this pattern, we will project this pattern to a one-dimensional response. So how to calculate the one-dimensional value? Actually, this one-dimensional feature value is set to the intensity sum of the white area might subtracted by the intensity sum in the black area. Okay, so this is the one-dimensional output. It can project one particular sub-window, including face or non-face, into a one-dimensional space. Okay, you can realize that why rectangle feature is very useful. This is the region of human eyes. So the intensity is lower in this region. So you can expect that the intensity sum of the white region subtracted by the intensity sum of the black region. So you can expect that the feature vector, the feature value is high, is high for face pattern, but for non-face pattern, there is no such property. So here is another. Here are the other two examples. It can be used to leverage the distribution, intensity distribution in the face pattern and the symmetric property of a human face. Okay, this is the meaning of rectangle feature. Is there any question? Let's have a 10-minute break.
老师，你现在没有声音哦。
现在是下课休息10分钟，我刚刚有讲，现在下课休息10分钟，现在12点，我们休息到12。
抱歉，刚刚可能刚好没听到，不好意思。
OK。
可是我想问一下，可是有听过就是 ADA Boost， 然后用 Binomial Log ID 也可以达到类似效果的文章吗？
Hello, hello. Let's get started. So, in this slide, I have talked about how to use a single rectangle feature to project a window. It could be a face or non-face window to a one-dimensional response. It is used to control one particular dimension of this feature vector of this pattern. Okay. So in the following, let's talk about how many rectangle features we have in a pattern of resolution 24 by 24. For simplicity, let's consider type A rectangle feature. This is a two rectangle feature. We use W and H to denote the width and height of a single rectangle. And this is a two rectangle feature. So the width is 2W and the height is H. So let's look at how many let's first consider this term. How many possible locations in a row? Since the size of this window is 24 and the width of this two rectangle feature is 2W, so the number of possible positions in the row is 24 minus 2W plus 1. Okay, so this is how many possible locations in a row. Similarly, let's consider how many possible positions for such a two rectangle feature in a single column. So it is 24 minus h plus 1. Okay, layer multiplication is used to indicate the number of rectangle feature of size with a rectangle size hw by h. However, we can consider different size W range from 1 to 12 because this is a two horizontally connected rectangle feature. So the possible size is 12. And H value ranges from 1 to 24. Okay, so there is a two symmetric rectangle feature. One is horizontally connected and the other is vertically connected. So the leading coefficient is 2 because we have two types of such rectangle features. Similarly, we can calculate the number of three rectangle feature and four rectangle feature using a similar way. So it turns out that the total number of rectangle feature is 160,000. It's more than 160,000. So for pattern of resolution 24 by 24. This rectangle feature project this pattern into a higher dimensional space. The dimension is more than 160,000. Actually, the rectangle feature, as explained here, it is useful to separate phase and non-phase. But there are too many rectangle features. In this situation, Viola and Jones use ADA Boost to select a small subset from such a huge pool of rectangle feature to control the phase detector. Okay, so let's record the property of boosting. ADA Boost or boosting is a classification scheme that work by combining weak learner into a more accurate ensemble classifier to a strong classifier. So a weak learner is only required to be better than chance or better than random guess. Training a boosted detector consists of multiple iterations. So it is an iterative iterative optimization process. During each iteration, we select one weak learner that does well on the example that were hard for previous weak learner, and the hardness is captured by weight attached to the training example. Actually, this property has been explained in the previous two sessions. So what I said is that we have knowledge about AWS. We also have some prior knowledge about phase detection. We project a 24 by 24 pattern into a high dimensional space with the feature number more than 160,000. So it is a very high dimensional space. It is impossible to learn a classifier in such a high dimensional space. So in this situation, AWS helped. This is the AWS algorithm. AWS is used to control strong classifier by iteratively selecting weak learner. Previously, we say how to use a rectangle feature to calculate the feature of a 24 by 24 pattern. So in this slide, I would like to link the relationship between weak learner and a rectangle feature. Via this equation, you can find that a rectangle feature ft, is used to control one weak learner. So since we have more than 160,000 rectangle features, it turns out that the candidate or the pool of weak learner, in this pool, there are more than 160,000 weak learner. We have so many weak learner candidates. Not all of them are useful, and not all of them are complementary to each other. In this situation, we can use AWS to select the powerful and the complementary weak learner from this huge pool. So in this slide, I'm going to specify how to use a rectangle feature to control a weak learner. A weak learner is a binary classifier. Given a 24 by 24 pattern as the input, we want to predict if this pattern is phase or non-phase, positive or negative. So let's look at how to use rectangle feature to carry out classification. We know given a sub-window of resolution 24 by 24 as the input, rectangle feature will project this window into a one-dimensional response. Okay, by consider a threshold So we can use the threshold to separate the response into two decision region. The first one is positive, and the second one is negative. So together with the threshold, a rectangle feature can be used to control a weak learner. However, this is the inequality. If we want to control the direction of this inequality, we can consider one additional learnable parameter, PT. It is called parity. Parity, PT, text value, either +1 and -1. It is used to control the direction of the inequality. If PT is 1, in this situation, PT can be ignored. In this situation, FT of X is larger than threshold. For this pattern, it is predicted as phase, otherwise non-phase. If PT take a value of -1, its effect is to change the direction of the inequality operator here. Okay, so so via this equation, you can realize how to control a poor of a weak learner based on our prior knowledge about one particular problem. 在这页投影片里面有一个关键，就是呢，我们这边呢可以把刚刚所定义的一个 rectangle feature 把它转成是一个 weak learner。那我们刚刚讲这个 rectangle feature 呢，总共有超过16万个所以呢，我们这边也有超过16万个 weak learner。那这个16万个 weak learner 就组成了一个很大型的一个 pool。那这些 weak learner 里面有一些可能不太好用，有些也没有什么互补性，所以 AWS 在这种情况之下就相当的有用。它可以从这个很大型的 pool 里面呢超过16万 candidate 里面呢，去选择，例如说100个或50个有用的，把它选择出来，而且把它做一个结合。那这一个例子也是在跟大家讲说。实际上 AWS 相当的 general， 你在处理你的各自的领域的问题像这边可能有人在处理 NLP， 有些人在做 speech recognition， 有些人是在做其他 AI 的领域，那你总是可以呢把你的这些对你那个领域的特有的这些知识，例如说一些 prior knowledge， 让它变成是一些有用的 weak learner 的 pool。那我这边举的例子是因为我是做电脑视觉的，那在做人脸辨识里面我们总是可以设计一些对人脸的侦测或人脸辨识比较有用的特征，例如说这种 rectangle feature， 然后去形成了一大堆 pool。那这个 weak learner 怎么用呢？后来我们就可以用 AWS 来选这样子。So how to use AWS to carry out face detection? Actually, we define the weak learner based on rectangle feature. One rectangle feature can be used to control a weak learner candidate. So we know AWS is an iterative algorithm. So at each iteration, we need to select one particular weak learner. So this is the task to be conducted in a single iteration. We need to evaluate rectangle feature on each training example. For each rectangle feature, we want to control the corresponding weak learner. So you need to, based on the example response, to determine the best threshold and the parity to minimize the weighted error. So this is the task of each boosting iteration. As you could see, the training process is slow because the computational complexity of training is high. It is a big O of M, N, K. M is the number of iterations. If we want to train a strong classifier with capital M weak learners, we need to run the process. We need to run the process with M iterations. Actually, we need to calculate the weighted error. So we need to the complexity is proportional to the number of training example. N is the number of training example. Also, we want to select the best weak learner at each iteration. There are total k rectangle feature, and there are k weak learner candidate. So the complexity is proportional to m, and k. So the complexity is high. After given the training data of phases and the non-phases, we have the two training data of the two classes. We also have the pool of the weak learner constructed by using rectangle feature. We can run ADA boost algorithm. Actually, this is the first two weak learners selected by ADA boost. So it is intuitive weak learner. It is to leverage the intensity distribution over the region of human eyes. And the list consider not only human eyes, but also consider the region of north. Okay, so this is the first two selected weak learner. If we run ADA boost with 200 iterations, we will construct a face classifier with 200 rectangle features. So this is the performance expression for face detection. We need to consider the detection rate and the false positive rate. We want to maximize the detection rate and minimize the false positive rate. So it is used to the performance is expressed by using the so-called receiver operating characteristic curve. Okay, so this is how to use ADA boost to select useful feature to carry out face detection. With some advanced design, this process can be carried out in real time. So this is the first real-time face detection. Here are some face detection results. There is a misdetection, but in general, Viola and Jones face detector provide good performance in many evaluation data set. In the following, let's talk about widely used machine learning methodology, a simple and effective machine learning methodology called the decision tree. Decision tree is simple and useful, but it tends to overfitting, and it is not very robust. So we can use Bayesian random forest or ADA boost to combine many decision tree to make decision tree more robust and more accurate. In the following, let's talk about how to construct a decision tree and how to apply decision tree for classification. Decision tree is a hierarchical model for supervised learning. It implements a divide and conquer strategy for classification and regression. Actually, decision tree can be used for not only classification but also regression. The most important feature of a decision tree is the divide and conquer strategy. I will provide two examples in the following slide. Since a decision tree is a tree, so it is it is composed of several nodes and edge. For nodes, there are two types of node in the decision tree, including the internal decision node and the leaf node. Let's look at the definition of the two types of node in the decision tree. For each decision node, M, we use M to denote one particular decision node. This decision node is associated with a decision function Fm of x. This function takes one particular data point as input, and its output is used to indicate the discrete outcome labeling the branch. This is an internal node. For each internal node, there are some following branches. So how to determine the branch for one particular input data point? I guess we use this function. For internal node with two branches, branch 1 and branch 2, we fit x into the function f of x, and it can be used to determine which branch this data point belongs to. Okay, so this is the goal of decision node. A leaf node is associated with a constant or a label. A constant is the regression value, and the label is for the classification classification class. Okay, a leaf node is a terminal node, so there is no further split. It itself is a leaf, so there is no following branches. So this is the difference between decision node and the leaf node. Decision node is internal node. There are some associated branch of some subtree, and the leaf node itself is a leaf, so there is no following branches. Given an input data point, a test is applied at the decision node at root. For testing data point, we fit this data point into the root of this decision tree. We know that the root of decision tree is our decision node, so we can determine one of the branch is taken depending on the decision function. So the process is recursively carried out until a leaf node is reached. So this is the property of a decision tree. I know it may be very ambiguous if we just look at the definition here. So let's consider one example. You can use this example to match the statement given in this slide. Okay, so this is a two-class. Let's consider two-class classification problem, and all the data points lie in the two-dimensional space. The first dimension and the second dimension. We also use color to indicate the class of each data point. This is a classification problem, and we want to use a decision tree to carry out the classification task. Okay, so we start from the root of this decision tree. We know the root of decision tree is a decision node. There is an associated decision function. So this decision function takes one particular feature and one particular threshold into consideration. So this is the so-called decision function. This decision function mentioned that it checks if the data point at on the first dimension check the value. It checked if the value is larger than the threshold W10 or not. So this is the first dimension, and suppose the threshold W10 is here. So based on this threshold, we can separate the input space into two regions, larger than the threshold and smaller than the threshold. Okay, so based on this binary function, there are two possible output. So we will have two branches. Let's talk about the simple branch. In this case, for this branch, collect data point that does not satisfy this decision function. Okay, so the answer is no. So it is on the left-hand side of this threshold here. As you can see, all the data point of this region belonging to all the data point of this region belong to class group. So it is pure. All the data point in this subtree belong to the same category. So we reach a leaf. There is no need to further split the data set because all the data point reaching this node belong to the same class. Okay, so we assign a label for this leaf node. We say for all the data point reaching this node belong to a class C1. So let's look at the another subtree or another branch here. In this branch, it covers this data point. Okay, so these data points are not pure because they do not belong to the same category. Some of them belong to category red and some of them belong to category blue. In this situation, a further split is required. So in this situation, this decision node consider this decision function x2 larger than some threshold W20. So it consider the second dimension with some particular threshold. So it further split this region into two subregions, above the threshold and below the threshold. So there are two corresponding branches. For the branches of yes, so it is pure. So a label is assigned to this class, C2. Similarly, C1 is associated to this branch. So this is the example of decision tree. As you could see, a decision tree is composed of several decision nodes and some leaf nodes. For testing, suppose we are given a new data example. We will fit the data into the root of this decision tree. According to the decision function, we will assign this data point to one of the two branches. The process is repeated until this point reach one particular leaf node, say this one. We will get the classification output. This is how a decision tree works for classification. For regression problem, for each leaf node, we don't associate a class label to each leaf. Instead, we associate regression value to a leaf node. Okay, so decision tree can be used for classification and the regression. A decision tree implement divide and conquer strategy to carry out classification and regression. After talking about the mechanism of a decision tree, our focus will be how to control a decision tree given a set of training data. Because a decision tree is often used for supervised learning, so the training data come with the feature vector and the training data have feature vector and the ground truth label. In the following, we use classification as the example. So Tn, the ground truth of xn, it is a discrete value. It is used to indicate the ground truth category of the input feature vector xn. As mentioned in the previous example, a decision function each decision function employs some particular feature with some particular threshold to carry out the decision function. Okay, but there are many features and there are many thresholds. So there are many different trees even for the same training data as the input. Our goal is to find the most compact or the smallest decision tree among all the candidates. So we can minimize the tree size, and the tree size can be measured as the number of nodes in the tree and the complexity of the decision node. We want to have a compact decision tree. However, it can be proved that finding the smallest tree is NP-hard problem. So it is impossible. It is impossible to find the optimal smallest decision tree for some particular task in general. So in the literature, we don't search the optimal decision tree. Instead, in practice, a greedy algorithm based on local search are used to construct a reasonable decision tree in reasonable time. In the following, I will talk about how to construct a decision tree based on a set of training data. Before talking about the tree construction, let's specify some criteria used in tree construction. We say starting at the root with complete training data, we look for the best split that divide the training data into two or multiple parts. In the literature, multiple parts are often called a different branch or a different subset because after this decision node, the whole training set will be divided into different subsets. Or this decision tree in this node, there are some following branches of the decision tree. So the three terms are interchangeable in the literature of decision tree. The splitting is applied recursively with the corresponding subset of training data until a certain criterion is met, at which point a leaf node is created and labeled. Let's look at the meaning of the criterion here. With the statement describes that the splitting function is recursively applied because in each decision node, we need to split the data set into several subsets to yield the corresponding branch. So how to determine if this process should be recursively done or should be stopped at a certain moment? So let's determine. Actually, we can make a decision by consider some particular criterion. So the first criterion is that this data subset is pure. For a node, it has several data points. If all the data points reaching this decision node regionless node belong to the same category. So we say this data set is pure. We don't need to further split this data set because we can make a decision and all the data points belong to the same category. Okay. The second criterion is about maximum tree depth. We want to have a small decision tree. So we can enforce this requirement by setting the maximum decision tree depth. For example, we say this decision tree, the maximum value of the maximum depth of this decision tree is 5. So if we recursively split the decision node, and in this situation, once we reach the 5th level of this decision tree, we reach the maximum tree depth. In this situation, even the data subset is not pure, we need to stop the splitting process. So this is the second criterion. The third criterion is about the number of data points belonging to some particular node. We say if we want to make a split, so it is like a classification problem. If we don't have sufficient training data, we will overfit this data subset. So to prevent this issue, we can predefine the minimum number of data points for a further split. Say 20 example. If a node consists of less than 20 example, we further split is not allowed. So this node will become a leaf. Okay, so this is the third criterion. The fourth criterion is widely used. The information gain is less than a threshold. We say at a decision node, we can further split the data set into 2 subsets. If after the splitting, the data are still hard to classify for each of the two children. So in this situation, there is no need to have a further split. So here are some criteria to stop the recursive process for tree construction. Well, let's look at the property of the internal node of the decision node. A decision node can be divided into 2 types according to the attribute or feature used to control the decision function. We say univariate decision node use a single feature or a single attribute to control the decision function. For example, if this single feature or attribute is real value, so it is a numerical value, so the decision function could be given in this form. Xi is large than some particular threshold Wm. So according to this statement, we can split the data point into 2 subsets. One subset satisfies this constraint. The other subset doesn't. So this is numerical univariate decision function. Also, in some application, the attribute can be categorical. Suppose they are impossible categorical values, and if we choose this data dimension to control this split, it will be a n-weighted split. They are n following branches. Compared to univariate decision node. Multivariate decision node use all attribute to control the decision function. Okay. In practice, we often use univariate decision function for simplicity and efficiency. Okay, let's talk about how to, in the following, I'm going to specify how to determine the optimal spread for each decision node. So it is required to introduce some notation. We want to estimate the goodness of a spread for classification. So actually, the goodness of a spread is relevant to impurity or uncertainty. So we are going to define we are going to introduce how to compute the impurity or uncertainty for a data subset in a decision node. As we say, a spread is pure if after the spread for all branches and all instances choosing the same branch belong to the same class. In other words, this spread is perfect. After this spread, classification can be carried out with 100% accuracy on the training data. If the spread is not perfect, we can still estimate the goodness of this spread by referring to impurity. Before talking about impurity, we need to give some notation. We focus on one particular internal node, M. We use M to denote this node. And the MM is the number of data points reaching this node. Okay, please remember the meaning of MM. It is the number of data points reaching node M. Let's consider another notation, NMK. There is a superscript here. K is used to indicate category. So the meaning of MNK is that the data point that reach node M and belong to class CK. So this is the meaning of MMK. Based on MMK and NM, it is intuitive to define the probability here. Probability PMK, it is intuitive to define as MMK by MM. So the meaning is that M is the certain node M, and the K is the particular category. So this is the probability for data point belonging to class K and the reaching node M. Okay, so it is an intuitive definition. So node M is pure if all data point it has belong to the same class. In this case, node M is a leaf with the class label. However, if this node is not pure, we need to calculate its impurity. So let's consider the measure of impurity. In the literature, we often use entropy function to measure the degree of impurity or uncertainty. Here is the definition of entropy. This is the definition of entropy. Let's consider a particular node M. IM is the entropy on node M. It is defined as this part on the part on the right hand side of this equation. A layer is a minus. There's a negative sign here, and we have some operator. This operator consider all possible classes they are capital K classes. So lowercase k is used to index every possible class. Inside the sum operator, we calculate PMK log PMK. So this is the definition of entropy. It is used to estimate the degree of impurity. By definition, 0 multiplied by log 0 is defined as 0. We will use this definition. For some particular class K, if there is no data point belonging to class K and reaching node M, in this situation, PMK is 0. 0 log 0 is defined as 0. Use this assumption to calculate entropy. For the other class, we can calculate this as usual. Okay, so let's look at the meaning of entropy. Larger entropy means that data are more uniformly distributed over classes. So large entropy means high level impurity. This is not the case we prefer. In this situation, it is very difficult to carry out classification. Data points belonging to this decision node, it is not predictable because there is a high entropy and the degree of impurity is high enough. Let's look at some particular example for two-class classification problem. So the entropy is composed of two inputs. For node M, we need to calculate PM1 and PM2 because they are two possible categories. In one extreme, all the both two categories with probability 0.5. In this situation, I of 0.5 has the maximum value. On the other hand, in the situation of purity, in the case of pure case, I of 10 and I of 01 are equal to 0. This is the minimum value of entropy. So in general, let's consider one class is the probability of one class is P. The other class is 1 minus P. This value is increasing when the value of P is between 0.5 and 0, and is decreasing when the value of P is between 0.5 and 1. Okay, so this is the definition of entropy. 各位同学好，我们这边讲了这个 function 叫做 entropy。那这个是一个在 decision tree 里面相当重要的一个指标。那这个指标呢是用来判断说，这个目前这个 decision node 到底呢它拥有的资料适不适合拿来做分类。那它的定义的方式就长得像这样子啊，比如说这个小写的 m 是 DM 跟 node 的 decision node 的意思，那 K 呢是代表特定的一个 class K， 那总共有大 K 个 class， 所以对每一个 class 小 K 我们都要计算PMK log PMK， 那最终加起来了以后，前面还有一个负号，那这个是用来衡量这个目前到达这个点的它的乱度 entropy 是多少。那我们可以想象如果呢今天你要做分类，那如果呢每一个 class 它的class 的分布是一个均匀分布的，那其实你都没有办法做任何的分类的结果比如说我们现在在做这种天气的分类，那总共有4种可能性：晴天、阴天、下雨或下雪。那如果每一个几率都是 25% 的话，那其实你根本就没有办法做任何的预测，因为每一个结果通通都是一样的。那在这个情况之下呢，你这个大 K 就等于4，那 PMK 呢就等于 0.25， 在这种情况下，你所算出来的 entropy 是最高的，所以 entropy 高代表不好分类，代表呢我需要呢最好可以再做一些 split， 然后可以去得到更好的结果。那反过来讲呢，如果当你的这些分布呢是很集中在某一个特定的 class， 例如说呢，晴天的机会有97%，那其他的3个阴天、下雨或下雪的几率都只有1%。那在这种情况之下，你就很好做分类，你可能也就不太需要再做进一步的 split。那这种情况之下呢 ，entropy 在这种情形呢，它是很接近0的，就达到它的最小值，就代表它最纯粹，然后最好做分类。Okay, do you have any question about decision tree and entropy? I don't think I have sufficient time to describe the information game. 今天的课程AWS 或者是使用 AWS 做人脸侦测，以及刚刚讲的 decision tree， 或者是这个entropy， 有没有任何的问题呢？的话，那我们今天课就上到这边。我们下个礼拜还是线上授课。如果我要改的话，会在公告会在寄群组就是在13上面寄信给大家。然后助教告诉我说，他这个礼拜在期中考，所以他原则上应该是下个礼拜1或下个礼拜2会公布作业2的成绩这样子。So if there is no further question, it is about time to raising up. TA told me that they are going to announce the grade of homework number 2 next Monday or next Tuesday. Okay, see you next week. 有同学在问这个我看一下。录影应该是不会公告了，就是没有必要把它公开嘛。你有什么特殊的需求吗？你不是都已经参加了？我没有听到你的回复。如果你再写信给我好了哈。那我们今天上课就上到这边了，谢谢大家的参加。